All right, we've come to the final video in the MPLS technology, and that is understanding MPLS VPNs. What we're going to talk about is how this technology, MPLS, has been applied to reshape the way that people understand WAN links and site-to-site connections between their offices. So what we'll walk through is the concepts behind, first off, traditional VPNs. And I'll tell you right now, it's not what you think. We'll then look at how MPLS VPNs deviate from the standard and really define a new way of connecting for us that's much more flexible and how communication works in that model. Finally, we'll talk about two huge new terms, route distinguishing and route targets, that allow us to well, I guess I'll leave that discussion for them. We'll understand how these MPLS VPN connections work. Let's get going by talking about the two traditional categories of virtual private networks. And right at this point, it's time for a nice paradigm shift. I'm sure just like me, when you hear about VPNs, you think about, oh, well, I'm connected to the internet and I do a VPN over the internet to maybe my company so I can work from home. Or maybe I have a site-to-site VPN going between two offices across the internet. Now, that is one definition of a virtual private network, but it's actually not what we're talking about at all here. We'll talk about IPsec-based VPNs and all of those fun things in upcoming videos. These are virtual private networks through a service provider. Here's where the paradigm shift comes in. When you get a dedicated T1 line between Arizona and Nebraska, that is a VPN. When I have a frame relay connection going through the cloud on a virtual circuit, linking up Taiwan and Canada, that is a VPN. Now, it's not how we traditionally think about VPNs with encryption and IPsec and so on, but if you really sit down and ponder it, you're going through a service provider network consisting of many routers. It's actually a virtual private network, being that the service provider is guaranteeing you that that link, that T1 line or that virtual circuit through frame relay or ATM, is not going to be seen or used by anybody else. It's quote unquote your line, but really it's going through their semi-public network because many other people are using that. So think about VPNs rather than internet connections and IPsec. Think about them as your traditional T1 lines. Your connections to the internet are a VPN of sorts. So first off, we have two categories of VPNs, and let me hit those directly. Overlay VPNs and peer-to-peer VPNs. I'm almost tempted to blend these in and say there's two categories of WAN connections, but I don't want to go that broad because then we get into different physical implementations. Really, these are just things that let you connect sites. An overlay VPN is traditional point-to-point links or virtual circuits between customer sites. Those are considered overlay VPNs because you're really overlaying a virtual private network, a line, through a service provider's network. So you see right here on this little diagram next to it, that's a full mesh overlay VPN, meaning all of these sites are quote unquote directly connected together, even though they're not directly connected because they're going through quite a number of routers in between as they hit the service provider network. That is an overlay VPN is what people traditionally will call a dedicated line. That's my bandwidth, or whatever term you want to put on it. Now, peer-to-peer VPNs aren't as common, and you usually see it in very, very large customers or very, very small, depending on how they're working. Peer-to-peer VPN means the service provider integrates with the customer network. You don't see this implementation very often. But this is where the client's network is part of the service provider. The service provider sees the routing table of the client, passes the routing table of the client to other sites and so on. Just like you see right here, we have two branch sites that are going through a 2600 router through a carrier's frame relay network and hitting some router over here and linking up to the other side. The difference here on a peer-to-peer VPN versus an overlay VPN is in an overlay, the carrier is invisible, right? They essentially bring in a physical connection to you and they say, oh, here's some Delcy information, or use this PPP encapsulation, and it's quote unquote your line. But I'm trying to explain this in a way that kind of shifts your mindset. It's your line, but is it really? I mean, you're going through a service provider, right? So really, it's their line. You're just borrowing it, and they're telling you that they are not looking at any of your data. And hopefully that's true. We just have come to trust service providers that they don't do that kind of thing. And I would say that they don't. Mostly. Now, the peer-to-peer VPNs, on the other hand, is where the service provider says, okay, we'll actually not just ignore your data. We'll look at your data and we'll pass your routes and let you have routing tables through our networks. In very, very large organization, it makes multiple sites look as if they were one big site. And in very small organizations, these two branch sites just communicate as if they were connected on the same network because the routing table passes through the service provider. It's almost like managed routing. They're managing all of the routing. Now, the drawback. With overlay VPNs, I guess I should give you the positive. These are well known. I mean, people know about overlay VPNs. It's what they call WAN links, you know, point-to-point T1 lines, DELCs, and so on. They know how that works. With peer-to-peer VPNs, it's good because you have perfect routing between the customer site. The service provider is going to provide the best possible route to get there. It's easy to add another site to that because the carrier is like, yeah, let's just bring them into our routing table. But the drawbacks, let's talk about the drawbacks of the traditional VPN model to connect sites is, first off, with the overlay model, to really have connectivity like this, it's going to be costly. That's a full mesh that you're looking at on the screen. You have to purchase multiple virtual circuits, and it's exponential. The more sites you have, the more virtual circuits you have to buy, or the more dedicated T1 lines between sites. You could use a hub and spoke topology, but that has drawbacks of delay as we're going through the central site, and latency and bandwidth being eaten up for traffic that really, you know, all goes through a central site. And you guys know what a hub and spoke is, where everything kind of points to one location. And you have to provision this on a site-by-site basis. On the peer-to-peer VPN, you can already start seeing some of the drawbacks. The client is totally reliant on the service provider, that the service provider fully understands their routing protocol, that the service provider doesn't let their IP address scheme get tainted with other managed solutions that they're offering, and also the service provider runs the challenge of addresses. They're seeing customers' routing tables. So this whole private addressing thing kind of slips away because the service provider now has to manage those addresses and only use them once because they're part of the routing table. They're not using NAT anymore to hide them from the sites and so on. So they really have to be on the game, and there may be some points where a new office comes in or a new customer, and they go, yeah, we're using 10.1. I'm assuming you can use that. And the service provider says, oh, no, sorry, one of our other customers is already using that. You're going to have to change your whole IP addressing scheme on the inside of the network. How many clients do you think act fondly to that one? Not many. So with our traditional VPN model, with our traditional way of connecting sites, there are problems. Now let's talk about how MPLS technology can change the way these VPNs work. Again, after shifting your whole paradigm of what a VPN was in the first place, now let's shift that paradigm yet again. MPLS allows you to have an amazing connectivity style between your sites. The sites feel as if they're directly connected. The big benefit of MPLS VPNs is the service provider network feels like it's your network. Remember that concept I just talked about of peer-to-peer VPNs where the service provider actually participates in your routing? That's what MPLS VPNs do. So, for instance, I have all these customer ones right here. Customer one will peer with its neighboring service provider router using whatever protocol they want. You know, throw out RIP, throw out EIGRP, and advertise the routes in. And then this router peers over here to yet another service provider router that peers with the customer one network on this side, and those routes are replicated in, and likewise, you know, you have this router tied in here and these are tied together. The customer network feels as if it actually has 6 routers that it manages because the routing table propagates to the service provider network as well, and they have their own, you could call it, virtual private network through the service provider world. That's the same thing as we talked about with the peer-to-peer VPN, but MPLS VPNs make it feel as if the customer has their own router at the service provider. Meaning these routers, the service provider is not going to provision a router per customer because you can imagine they would definitely run out of a budget real quick. But these routers, to the customer's perspective, feel as if it's their router because they only see their routing table on there. And these routers only propagate routes from the customer site back over. I mean, you can see there's another customer too right here, which maybe ties in to the same router, just like this. Right? But the way these MPLS VPNs work is that router will never allow customer 2 routes to be seen over on customer 1. As a matter of fact, this router thinks of customer 2 routes as almost a separate router than router 1 within itself. Now we're getting weird. The idea of this is something known as VRF, Virtual Routing and Forwarding, meaning that these routers, these MPLS routers, let me just give this one a label. We'll say router A. Router A is able to run multiple VRF instances. Have you ever seen on a Windows PC the product called VMware? Or if you're on Macintosh, it's called Virtual PC or Parallels or some other thing like it. If you haven't, it's a product that allows you to run multiple operating systems inside of your one. So maybe you have Windows, but inside of Windows you also have Linux running, to where it's almost like you have 2 computers in one. That's what VRF is all about. It allows you to almost run multiple routers in one. Instead of having separate iOSs running, it's not like that's where the VMware analogy breaks down. VMware literally carves out memory, carves out resources from the processor, and says, okay, we are running a completely new operating system, new BIOS and everything. Instead of doing that, the router just maintains separate routing tables and forwarding tables per customer. So it's not like it's eating up the resources to run the iOS multiple times. It only runs the iOS once. It just has these virtual routing tables that it uses to propagate amongst each other. So routers A, B, and C, maybe they all have 50 different VRFs inside of them for 50 different customers, each one maintaining a separate routing table for each unique customer instance. These MPLS VPNs also eliminate the problem of duplicate address spaces, meaning in the peer-to-peer VPN model we talked about originally, if 2 clients were using the same address space, then one of them would have to change in order to have the service provider provide them peer-to-peer routing, because the customer's routes would permeate the service provider's network and could only be used once. Well, with MPLS VPNs, you can have overlapping address spaces between multiple customers because the VRFs make them appear as if they were different routing tables. Now, this is a closer look at the service provider network. You see that we have PE, which stands for Provider Edge. That's the symbol that Cisco uses as the LSR edge, if you will, to where that's the last label switched router that we have in our MPLS networks. And then right in the middle of the service provider networks are our P routers. Those are provider routers. Those are the ones that are at the core. They don't actually touch any customers. They run the service provider's network. The PE routers are the ones that will communicate with the customers and receive their routes and put them into their own little virtual routing tables for those customers, to where, for instance, you can see here again, customer 2 would just have this virtual routing table going between these 2 PE routers that only they are able to see and share. Those addresses are kept completely separate from customer 1. Now, the P routers do not see customer routes at all. Here's the wild thing. Customer routes are encapsulated inside of this shell that only the edge routers and the customers will see for those instances. For instance, think of it this way. The customer 1 router sends in some routes. As soon as it reaches this first PE router, we'll just say we have these routes, The first PE router will stick a big encapsulation on it, and I'll tell you what that is in just a moment, that says, these belong to customer one. And that little tag goes throughout the service router network. Customer one routes, customer one routes. This PE gets it and says, oh, well, I've got a customer one. Let me go ahead and tear that label off and send it out to my customer one. You know, this guy gets, he's routing for two customer ones and receives it, rips off that customer one tag and sends it out to this customer one. The P router never has to rip off that big one tag because it's in the middle. It's not connected to customer one sites anywhere. Same thing happens with customer two. It sends some routes in via RIP or something like that. You have the routes, and those are encapsulated with a big two or something like that. And it comes in and goes throughout the network, and it just looks like a normal packet to all the rest of the service provider routers. It's like, hey, it's, you know, it's got a beginning, it's got an end. And when it gets to this endpoint, it goes, oh, I recognize that label. Hint, hint. You see that? It says, oh, that's one of my labels. That's for one of my customers. Tear that label off and propagate those routes out to customer two. Do you see what's happening here? We're taking customer routes and we're surrounding them with an extra encapsulation that tags them as what belongs to that customer. So the provider routers never really see the customer's routing table except for the edge routers and only in those virtual routing instances. So these could be overlapping with different customers all day. You know, customer 2, customer 3, and customer 1 could all be using the same address space, but these routers don't care. They just know, oh, there's a big 2 label, let me rip that out and send whatever's inside over to customer 2, and that's where the routing tables get built on the customer. So it's a very powerful way to have these customer sites connected together, and we lose this whole, oh, I have to buy another virtual circuit, because as long as we're connected to the same service provider, hey, it's a pie in the sky. We've just added another router to our Ethernet segment is almost what it feels like, and it just suddenly gets populated with the routing table. Powerful stuff. It's exciting stuff too, because it's insanely complex, but at the same time addresses the needs that people have to make WAN connections even more flexible. So let's get into the new MPLS VPN terms. These are two new terms that are used to describe how they do exactly what I just described on the previous slides. How do they stick that big 1 on the front of those routes, or the big 2 to let it know what customer it belongs to? That is the job of a route distinguisher, otherwise abbreviated RD. A route distinguisher is a 64-bit tag, so it can be a very large value, that is just used to keep customers' advertisements and routing updates unique. Every customer gets assigned a RD, and the customers will have the same RD. For example, customer 1, they would have one RD that's assigned to that whole customer, and it could be a big customer. I mean, take a Intel or a Motorola, you know, with many sites all over the place. But if all those sites shared a single connection, meaning it felt like one big routing table, they would be assigned a single route distinguisher. That 64-bit value, it's arbitrary. It can be any number or combination that the service provider wants to do. So they can come up with their own numbering scheme or whatever they want for that route distinguisher. There's no, for instance, this is the way that all service providers assign those numbers, because it's on a per service provider basis. That's pretty self-explanatory. Route distinguisher, it's just a big label that we stick on the customer's route so that we know those belong to this specific customer, and uniquely tags them in the same way I described on the previous one. The route target, on the other hand, is a little bit more difficult to explain. What it does is it allows customer VPNs and connections from the customer network to be a part of more than one VPNs. For example, let me, I'm going to paste in a picture from my introductory slide. Let me see if I can find it real quick. There we go. This just being an MPLS VPN. Now, I'm not really concerned with the microscopic text all around there. I just want you to imagine that all of these clients right here, let me just run some circles around them. Let's say that these three, grab the right pen here, these three buildings are one client. This is customer 1. Okay, and then the rest of these buildings down here, just for ease of example, are all customer 2. Okay. Now the route distinguisher comes in to where there would be some unique 64-bit value that identified all of these customer 2 routes coming from all these offices. So as the routing updates and IP addresses come in, they're always flagged at the provider edge router right here with a little route distinguisher, some 64-bit value saying these are all customer 2, and vice versa for customer 1. But one of these things in this MPLS network in the middle here is shared between the customer, and that is the public internet connection. Maybe the service provider says, you know what, if you sign up for MPLS with us, you also will, of course, get an internet connection. So you can use us, one service provider, for your inter-site connectivity and for your internet connectivity to allow all of that to happen. But the problem is that whose site? Do we add this public internet router to? Do they get tagged with that route distinguisher or that route distinguisher? And the big answer to that question is it's actually both. That internet connectivity site between those two gets part of this route target. Now, a simple way of putting a route target is that it just allows multiple VPNs to be combined into one. It is defined in import and export values, just like I have in that final bullet there. What that means is with route targets, I get to define what VPNs will import their route into a customer network. For example, that internet example I just gave you, I would say I want to import the internet VPN route into both customer networks. So they would both get the same route to let them out to use the internet access. The export route targets says what networks are your routes going to export to. It's a little more difficult to explain, but let me just give you an example here. Let's say that customer 1 and customer 2, just like I had in that drawing right here, partner up and build an extranet between each other. And I want this office right here, let me just circle it. I want that office to send its routes to this customer VPN over here. Well, what I can do is I can have export routes with a route target tag that these are now valid to be exported over here to this customer network. So now customer 2 gets part of customer 1's routing table and gets sent over there. It's used for a lot of things, but it's really, as it gets more complex, allowing resources to be shared in the service provider realm. One more example I'll give you for that. Hot new thing that service providers are now offering is managed voice over IP services, to where they not only run the data network for the client, they run the phone network too. And they bring in a bunch of Cisco IP phones, but they maintain all of the routing intelligence, all of the call processing intelligence at their site from a cluster of, we'll say, call manager servers. We'll keep everything Cisco-centric here. Well, if multiple clients are using that same cluster, then that cluster, just like the internet access, has to be added to their VPNs. That's the job of the route target. Just think of it as collapsing multiple VPNs into one. As we wrap up this concept, let's take a look closer at the service provider network and look at the protocols that are making this happen. The beauty of all of this is that to the customer, it just looks like a normal network connection, and they can use whatever styles of routing protocol they choose. They can use RIP to advertise their routes into the service provider. They can use OSPF. If the service provider supports Cisco routing, which, well, they all do, then they would have EIGRP being an option. BGP could be used by the customer. Whatever they felt comfortable with to manage their own network. They could even say, service provider, could you just set up some static routes? I mean, we don't want to run a routing protocol. If they're that small of a client, then that's totally an option as well. The customer uses normal internal routing protocols to communicate with the service provider and advertise their route. Once you reach the service provider network, you see that protocol. You might think, oh, that's a new one. It's not really. It's actually BGP that the service provider uses to transport those customer routes throughout the network. It's just the MP in front of it stands for multi-protocol BGP. It's not a completely new deployment, it's just a tweaked version of BGP that allows us to put those route distinguishers onto the customer's routing advertisements. That's the one that contains the 64-bit field so that we can uniquely identify them. Now, I'm not saying that the service provider only runs multi-protocol BGP inside of their core. If you get into BGP, you find out that service providers have their own protocols as well. They might be running, between their internal routers, like OSPF or ISIS is a popular one for service providers to run because it's very tunable. The multi-protocol BGP just runs on top of that to carry customer routes between these provider edge routers. And once it gets here, it converts it out and sends it and says, oh, hey, I've got a RIP advertisement for you. Here is your routing table. Now you might be wondering as you look at this diagram, what's MPLS have to do with all of this? I've seen customer routing, I've seen multi-protocol BGP. Why is it called an MPLS VPN? Well, MPLS is actually the fabric that binds this whole thing together. It does two major things. As the route is received by the provider edge router, and the provider edge router sticks that label on there with multi-protocol BGP and begins to advertise that into the rest of the network, it sticks on a label to the front of it, an MPLS label right on the front, and that tells it what PE router to go to. Meaning it looks at the customer routes and identifies it with the 64-bit advertisement in there and then says, okay, that 64-bit identifier says that you should end up going to this provider edge router, which is maybe the other side of the connection. Maybe there's multiple packets sent out to multiple provider edge routers. Whatever the case may be, that's what the MPLS label does. Likewise, once it gets to the other side, as it comes into that provider edge router, it squeezes yet another label in there that says, this is the interface that I exit out to get to that customer. So as this provider edge router peels off the labels, it says, okay, this goes to me, I'm that provider edge router, and the second label says, I'm going to send it out, this interface, out to that customer who receives it. So all of these things have to tie together to get the customer routes exchanged and get exchanged fast. That's where MPLS ties in. It provides that whole fabric that's used for communication between the service provider core. The client never sees anything MPLS. That's the scoop behind these new MPLS VPNs. And that's about as deep into MPLS as we're going to get in this CCNP track. I encourage you, if you want to see more about MPLS, it's a very cool technology. That's where the service provider certification is, that CCIP, Cisco Certified Internetwork Professional, comes into play. So just to hit the high points, we did talk about traditional VPNs, the overlay VPNs, which is what we're all used to, pretty much overlaying on top of a service provider technology are private WAN links, and then the peer-to-peer VPNs, which was kind of a way service providers did MPLS style VPNs in the old days, but had huge limitations because of the address space issues that you would run into. We then talked about MPLS VPNs, which are the new peer-to-peer VPNs, allowing service providers to participate in customer routing, but eliminating the overlapping address issues. We talked about how communication works inside of that connectivity, where the provider edge routers speak to you using normal routing protocols and then translate you into service provider technology, which is MPLS and multi-protocol BGP. Talked about two huge new terms in that process, which was focusing in on the route distinguisher, a label that will distinguish all of your routes as being part of your customer network, and the route target, allowing you to share other VPNs, such as internet connectivity VPNs, voice over IP VPNs, where you have shared resources in the service provider. I hope this has been informative for you, and I'd like to thank you for viewing.